Thank you very much for the introduction, and thank you for the invitation, and thank you also everyone for coming. So yeah, I will talk about dynamical disorder and carrier localization in halide perovskites. And I will start with a bit of background, very brief, about these materials. And then I will have kind of two separate topics of the talk. First will be dynamical disorder in halide perovskites and how it affects the properties that we calculate, like band gaps, but also how it affects the interpretation of measurements. And then I will have a separate kind of story on charge localization, so polaron formation in these halide perovskites, where I will focus on some challenges in modeling and on results for thin halide perovskites. So with a bit of background, I suppose most of you already heard about halide perovskites. They are very exciting materials. For instance, for solar cell applications, and here is a power conversion efficiency chart as a function of time. So you can see that these solar cells based on halide perovskites are rising in efficiencies, and they are sharply rising. So there is a lot of interest in the community. And what are these materials? Here we have the simplest structure of a cubic halide perovskite with an AMX3 formula, where A is a cation, blue one here, M is a metal like tin or lead in the center of the octahedron, and then we also have halide atom X, the green one here. And these materials are very soft. I think everyone who works with them is aware of that. But this softness can affect quite a few things. For instance, we will have very strong dynamical disorder that will affect how we calculate things for the materials. But also, since the lattice is soft, it might be easy to displace it by the extra charges like electrons and holes that are generated by light. And then we will have polaron formation. So I will focus now on the first effect, which is the dynamical disorder. So it means that, which means that at finite temperatures, all the atoms will be moving quite strongly in the material, and this can affect how we should calculate things. Because as you know, most DFT calculations, most standard DFT calculations are done at 0 Kelvin for some average structure. We take a structure from a database, run one calculation and get a property, which might work well for very hard and standard materials like silicon, in which, looking at this scheme in which I represent here the average structure based on this perovskite with squares representing octahedra, in a hard material at room temperature we will have some movement of the atoms represented by tilting, but it will not be very far from the average structure. And then maybe 0 Kelvin calculations will be enough. And then in other materials, softer ones, we will have very strong movement. So at any time and locally, atoms can be very far from this, their average positions, like in halide perovskites, where calculations at 0 Kelvin won't be enough. And then other thing is related to what we want to calculate, which property, because as we can say that some properties are kind of linear with the displacements and some are not. And if we describe these displacements in a halide perovskite structure as tilting, which can be one way or the other, let's call it left and right, we can have a property where a measurement for one way of tilting will decrease a measurement value, and then the other way we will have an increased measurement compared to the average structure. So then the measurement, which is just the average of all possible cases, will match very well with the average 0 Kelvin structure. And this is the case for like structural properties. For instance, X-ray diffraction patterns will behave this way. But we can have also different scenarios in which any departure from the perfect average structure can lead to, for instance, increase in some property like here. And then the measurement will not correspond well to the average structure at 0 Kelvin. And then 0 Kelvin calculations won't be enough. And this is, for instance, the case for band gaps, a very basic property of a material. And to show you how it works for halide perovskites, I have an example here of a study when we compared band gaps calculated at 0 Kelvin for cubic structures of all these compounds that are shown in the table, and compared them with values calculated from snapshots from ab initio molecular dynamics run at various temperatures at which the cubic phase is stable. And so you can see, I will show you a video now, but first in this video we start with the cubic, perfect, very well aligned structures. A structure that you can see everything, all the octahedra are aligned, we have straight lines. And then we run MD, and immediately the atoms start moving a lot. From this, you can see that the materials are indeed very, very soft. We have a lot of movement, tilting, and so on. And this affects the band gap quite strongly. You can see the differences between the 0 Kelvin calculation and MD calculation from 0.5 to almost 0.8 electron volt. So very strong effect. But this dynamical disorder doesn't only affect like some singular properties of the material. It can also affect how we understand the structure, how we interpret experimental measurements. And here I wanted to show you a collaboration we have done with experimentalists that studied phase transitions of cesium lead bromide. And basically it's related to some confusion, I think there was in literature on the structure of these halide perovskites, because we can expect them as normal oxide perovskites to have low symmetry phases at low temperatures, and then go to high symmetry phases like cubic at high temperatures. And in some measurements at high temperatures, the measurements don't seem to represent the cubic structure. So I think that some people could think that these materials are not really cubic at high temperatures, they are something else. So my collaborators here used two experimental techniques to monitor the structure during heating. X-ray diffraction, XRD, and X-ray absorption, XANES spectroscopy. And in XRD, everything seems normal. At low temperature, we have some peaks, which then disappear when we go to higher temperature. So it's like a normal orthorhombic to cubic transition. But it's a bit more complicated when we have these more local measurements, XANES. So what they measure are spectra like this. And they don't really look at the absolute spectra because it's difficult. They look at differences. So here in the bottom, we have in black dashed line, the difference between high temperature and low temperature spectrum. And the first step to analyze this data is to compare with DFT calculations. We can calculate this spectra, which was first done at 0 Kelvin for the average orthorhombic and average cubic structure. And here is this result. As you can see, this blue line is basically opposite to the experiment, where we have a minimum here, we have a maximum, and so on, which could make an impression that this is not an orthorhombic to cubic transition based on this comparison. But what we decided to do here is to include this disorder. So we ran MD simulations at different temperatures, and then calculated spectra on the snapshots. And this difference then you can see from MD, yellow to red line matches much better the experimental difference, which means that this is exactly this transition orthorhombic to cubic. And also having MD trajectories, we can analyze a bit more why we have this confusion, what is going on in the material. And here I extracted angles between neighboring octahedra like this. So basically for the cubic structure, we have everything aligned. So this angle would be 180, here transformed to 0, basically in this plot. And then any tilting is a departure from this angle. So at lower temperature in gray, we have a distribution with two maxima, which corresponds well to this orthorhombic phase, where we have patterns of tilting, left, right, left, right. And at higher temperature, we have just one maximum, which corresponds to a structure which is on average cubic. But what we can also see here, that the distributions are very wide, and they are equally wide for the cubic, so high symmetry structure, and orthorhombic low symmetry structure, which means that anytime we measure anything local or calculate anything local, like the band gap, like X-ray absorption, we're just probing from this distribution, which for cubic phase and orthorhombic locally well, the structures are equally distorted. So this can lead to some confusion. Okay, that was all I wanted to say about this disorder. And now I want to talk a bit more about charge localization in these soft lattices that can deform easily. So what is this charge localization? I'm basically talking about polaron formation, which are trapped, self-trapped charges in a semiconductor that can appear. And basically, it's related how we think about excess charges. In the first step, we think about electrons and holes generated by light being in the valence band and the conduction band, and being delocalized in the material like shown here. But in polar materials that can be easily displaced, these extra charges can introduce deformations in the lattice and trap themselves, get screened from the surrounding, and well, look more like this. So this would be an electron polaron here with its deformation. And then if polarons are stable in a material, we will have also an additional energy level in the band gap. And this is basically where our extra charge will be placed. And from this scheme, you can already imagine that this polaron will affect energy alignments in these materials, because this is a new energy of our extra electron. But they can also affect charge mobilities or charge recombination. So it's very important to be able to predict in which materials we will have these polarons, how stable they are, where is the energy level, and so on. And first, I wanted to talk to you about some challenges we have in calculations of polarons in halide perovskites. So first thing, so I will talk here about an example of cesium lead bromide, in which we can find a polaron state for the electron around lead, like shown in the picture. So we can find that there is a possibility of having a polaron, but now we want to get its energy and so on. And first issue is that we cannot study polarons directly with semi-local functionals like PBE, because we have a self-interaction error in these functionals. And to treat it, we can use hybrid functionals, but we cannot also use any hybrid functional. We have to use an accurate functional for a given material. And we have been choosing these hybrid functionals based on a physical property, which is called physical condition, which is called Koopman's condition, which says that if we have a localized state in a material, basically its energy level should not depend on whether we have a charge or not. So what we do is we find this polaron, and for different fractions of exact exchange in the hybrid functional, we look at the unoccupied state and occupied by changing the charge of the simulation cell. And we found here that for this cesium lead bromide, we need to use 0.34 for the fraction, for which we find that at 0 Kelvin, without spin-orbit coupling, the polaron is more stable by 0.24 eV than the conduction band electron, which suggests that this polaron should be stable. But we have some other effects that are important that have to be taken into account in these calculations. So first one is spin-orbit coupling, a relativistic effect, which is very important for halide perovskites because we have these heavy metals that contribute to the conduction band minimum. So basically this would be lead d states in this material, which with spin-orbit coupling split into higher and lower level. So we have a new conduction band which can be much lower. And we could assume that the polaron is also on lead, so its level will also split and be stabilized. But what we found is that while it is true, the polaron is stabilized by less due to this relativistic effect than the delocalized electron. And now with spin orbit coupling at 0 Kelvin, we have a polaron that is by 0.07 eV less stable than the delocalized electron, which would mean that, well, polarons are not stable in this material. But this is still at 0 Kelvin, and we saw that temperature can change a lot. So to look at what happens at room temperature, we perform thermodynamic integration calculations, which give us now free energy differences. But to have this difference, we need to connect our two systems with a polaron and with the delocalized electron, which we do by diffraction of the charge, which is plotted here. And then we have energy versus conduction band minimum in this plot, which we can then integrate and get the room temperature stability of a polaron. And we find that temperature stabilizes the polaron by 0.21 eV, which put together with the spin orbit coupling result gives us a polaron which is by 0.14 EV more stable than the delocalized electron. So it seems that electron polarons should be stable in this material, and we also learned what are the challenges in calculating them. So we wanted to go a step further and study a larger class of materials, tin halide perovskites, which are interesting because now we replace lead, which is toxic, with tin, which is not toxic. So it's these materials are interesting, but also from computational point of view, tin is lighter than lead. So we have weaker relativistic effects that we know that they destabilize electron polarons. So we expected that they might be more stable. And this is what we found. We found electron polarons to be more stable now. And especially we found them to be stable when we have two electrons coming together. So when we have electron bipolarons. And what happens in many tin halide perovskites is that we start with this structure, we have two electrons and they form a bond between tin atoms and they push away one halogen atom. So here you can see the materials that we studied. We varied the halogen atom, the cation, and these bipolarons were always stable. So we have this negative energy here. They look kind of the same in all these materials. We have these bonds formed and halogen atoms being pushed away. And these bipolarons could be, I think, quite detrimental for solar applications, because if we have extra charges created by light, but they are very strongly trapped in a bond somewhere in the bulk, they will not easily go to the surface or the interface and contribute to, well, electric current, or they will not drive some reactions. And to check a bit further what these polarons do exactly in some devices, with some collaborators in Italy, we looked a bit further on at these polarons in dimethylammonium tin bromide, which is water stable and could be used for water splitting reaction. And basically what we found that they are also stable at the surface of the material, and they can have both positive and negative effect on the reaction. Because first, the charge localization will bring the charge to the surface where the reaction has to happen and be a driving force for the reaction. But if they are too stable, they may hinder the swift completion of the reaction, because the charge might want to stay in the semiconductor and not drive the reaction. So it's something that we can think about when looking for new materials, to find materials with polarons which are exactly right. And with that, I wanted to finish my presentation with a short summary. So I wanted to show you that halide perovskites are very soft, and the dynamical disorder can affect strongly the properties that we calculate or how we understand their structure. And then I focused on excess charges in halide perovskite that in some compounds can localize and form polarons. On the example of cesium lead bromide, we saw that there are some computational challenges when we want to calculate these polarons. And then for tin halide perovskites, we found that electron localization is especially strong. And with that, I wanted to thank you for your attention and thank all the people who contributed to different topics.